Hey everyone, this is Scott coming to you from Pivot. I wish I could say I was reporting to you from a trade show, as it may look like, but this is an image taken at a show where we had a tabletop sometime back. But what I did want to talk about is Chromanik Technologies, a close partner, and more specifically their bonding technology. What I'm going to do is dive right into a screen share. So bear with me as we move over to this now. I'm going to move a couple of notifications, get this out of the way, and get things going. We're off. So here we are. And by the way, I have some notes that I may refer to help keep this presentation moving. So we are Pivot. We work with Chromanik Technologies, and we're going to speak about the end capping technology for Sunniest, which is the fully porous material, and Sunshell, which is the coreshell material. So this is a breakdown of the Sunniest bonding technology. And so as you can see, there is a main silo reagent, and then there are two end capping reagents as well. And so we'll talk about it more going forward, but there's hexamethyl dichloryl trisiloxane as well as trimethylchlorylsilane, or TMS for short. But what we really want to highlight here is there is a high temperature reaction for the end capping, and that's at 200 degrees Celsius, or actually above that, so more than 200 degrees Celsius. And this is more of the bonding state of the Sunniest C18 on silica. So the end capping reagents move like a geometrid caterpillar, and these functional groups bond with the Silanol groups, and the TMS also bonds with the Silanol groups too. So there is Silanol activity control, and this is the Chromanik technology and one of the advantages of this. So looking at a typical no end capping C18, you'll see Silanol groups. So we have hydrated Silanol groups, which are the blue ovals, and we have the non-hydrated Silanol groups, which are the pink ovals. The hydrated Silanol groups do not absorb basic compounds and act more like an ion exchange, where the pink ovals do absorb basic compounds and do have an effect or an influence on hydrophobicity. So what about this Silanol activity control technology and the heat? So this more than 200 degrees Celsius causes the silica gel to become amorphous. And as a result, the Silanol groups combine to form a siloxane bond. And as a result, you do not see, as here, you do not see the non-hydrated Silanol groups. And as a result, we don't see the absorbing of basic compounds. We'll talk more in the next slides. But just looking at the ratio of residual Silanol groups, there's about 8 to 9 micromoles over meter square of Silanol group is said to exist on a silica surface. And then after C18 bonding, 2/3 of the Silanol groups exist as residual Silanol groups. So the ligand density is 2-3 micromoles over meter squared. So how many Silanol groups exist on a silica surface after C18 bonding and end capping? And as you can see over the years, it's become less. And so peak tailing of a basic compound by residual Silanol groups is blocked by end capping, even if 1/3 of Silanol groups exist on the silica surface. So let's go back to comparison here. So looking at a conventional end capping, you see the pink ovals, again, the non-hydrated Silanol groups, and they contribute as a polar site and make hydrophobicity of a stationary phase decrease. But if you look at the Sunniest end capping and Silanol activity control, as noted before, you can see that, again, there was the whole reaction of more than 200 degrees Celsius. You have the siloxane bond. You can see that this technology with the Silanol activity control is more hydrophobic. So what about carbon loading and retention factor? So the end capping reaction is more than 200 degrees Celsius, as noted here, the X degrees, which is the Chromanik column. And so looking at carbon loading at here, we're definitely at 7%, which is the carbon loading of C18. So carbon loading after end capping, in the case of the Chromanik column at more than 200 degrees Celsius, some of the C18 chains get cut off by the heat, as opposed to a conventional column, the C18 chains do not get cut off. But with that, with this high temperature, we get the Silanol activity control as compared to the conventional columns. So what does this mean? So retention factor here shows the retention factor is higher at 10.6 K as opposed to 9.5 for a conventional column. And you can see the layout here and the chromatograms as well. But what here is, so to compare a little bit more, or again, the retention factor is higher with the Chromanik technology. However, the retention time is faster with a conventional column a little bit. So when you're looking at retention factor, Chromanik proves to have an advantage. So what about relationship between retention factor and carbon loading? So again, looking at the Sunshell column, which is the Chromanik line, and using the Silanol activity control, the retention factor of this column is higher, despite carbon loading being less. And this is again due to the Silanol activity control and some of the relation to the previous slides. So let's look at more comparisons. So we looked at comparison of amitriptyline peak. And as you can see, we're looking at a Sunshell C18 column versus some of the other competitors. And these include Coreshell, Kinetics, AccuCore, Cortex, and Ascentus Express. You can see and we're looking at the mobile phase is acetonitrile and 10 millimolars of ammonium acetate at a pH of 6.8, and we're using a 4.6 by 150 column. And as you can see, the tailing factor of the Chromanik column fares better. The closest one would be the porous, again, based on this application. So what about stability? So if you look at this breakdown, we will look at the relative retention percentage and time. And we're using a column of 2.1 millimeter ID with a 50 millimeter length. Here are the comparative columns. If you have any questions, please let me know. But they're similar to the ones in the previous slides. If you look, even when the relative retention goes to 90%, the Sunshell column holds up very well at 120 hours. as compared to some of the other columns that are based on this are not as stable. And this is under stability under acidic pH. Now, what about stability under basic pH condition? So we're going to look at relative plate butyl benzene percentage and then elution volume in milliliters. We're looking at a pH of 10. Again, the column size is a 2.1 millimeter ID, 50 millimeter length. And you could see even as we reach up to almost 5,000 milliliters, the Sunshell column remains quite stable as opposed to some of the comparative columns. Now, what about the bleeding test using LCMS? And by the way, we have a lot of LCMS applications as well. Looking at the Sunshell C18 column versus a comparative column, this is the red, and this is on an ion chromatogram. And then to the right, we have a mass spec looking here between the minutes of 6 minutes to 8 minutes of a sample, looking at a column of 2.1 millimeter ID, 50 millimeter length, mobile phase of 0.1% acidic acid, and acetonitrile. You can see that the Sunshell column holds up quite well, and there's more bleeding on the competitive column. What about continuous analysis under acidic pH condition? You can see here. Looking forward, even if when you go, so again, this is a Sunshell column, 2.6 micron, 2.1 by 50 millimeter length. We're looking at a 0.1% trifluoroacidic acid, pH of 2 with acetonitrile. And even go into the 10,000th injection, you can see that the peaks remain consistent and hold up very well. In addition, the peak width doesn't change much, as you can see in the lower table here. Looking at the injection number as well as the width. What about continuous analysis under basic pH condition? And you can see here, this is a 2.1, again, similar 2.1 by 50 millimeter length, 2.6 Sunshell column. We're looking at a mobile phase of 10 millimolars of ammonium bicarbonate, pH 9.5 with acetonitrile. You can see even up to the 2,700th injection, the peaks remain pretty consistent. So in summary, the Sunniest Sunshell Chromanik bonding technology leads not only to separation without tailing for basic compound, but also a large retention factor. Additionally, this technology makes stability under both acidic and basic pH conditions increase. I look forward to hearing your thoughts. I'm going to unshare this. And again, looking forward to hearing your feedback. If you have any questions, please let us know. Thank you so much.